Okay, we're gonna go ahead and get started. Hello, everyone. My name is Kelly Dudley, and I'm with the News Center, and I'd like to welcome you to today's webinar entitled Powering Low Carbon Cement, Unlocking the Potential of Electric Arc Furnace. And we're so glad you could join us today. A video recording and PDF of the presentation you're about to see will be uploaded to the new website, newconcrete.org, following today's webinar. Attendees are in listen-only mode, and you will have an opportunity to ask questions in the Q&A dialog box at the end of the presentation. The ideas expressed in the following presentation are those of the speaker and do not necessarily reflect the views of the News Center, ACI, or its committees. As with all concrete mixtures, trial batches should be performed to verify concrete properties. Results may vary due to a variety of circumstances, including temperature and mixture components, among other things. You should consult your material, cement, and concrete professionals for design assistance. Nothing contained herein shall be considered or construed as a warranty or guarantee, either expressed or implied, including any warranty of fitness for a particular purpose. And now I'd like to introduce you to News Executive Director, Carrie Sutton.
Hey, good afternoon, everybody. Thanks again for attending this webinar. We're really looking forward to Simon's presentation. And I also have Sarika Sumanasuri. Sarika, do you want to say hi real quick? Just do a little introduction of our team.
Hello, everyone, and welcome to the webinar. And I'm Sureka Sumanasuri. I'm the Technical Director for NEO. So along with Kerry, I'll be moderating today's Q&A session. And we really hope that you find this session informative. And with that, I will let Kerry to introduce our speaker.
Thanks, Sarika. Our speaker today, Simon Blottavokel. And we appreciate you being here, Simon, and presenting for us today. Simon's with EcoSem. EcoSem is a member of NEWS, so we appreciate that and the support they give us. So Simon earned his PhD in geochemistry from the University of Toulouse in 2017. He specialized in slag cements during a postdoc at LMDC Toulouse, and his contributions to the understanding of slag reactivity were recognized with the Klaus Dickerhoff Prize for Young Scientists in 2023. So congratulations for that, Simon. What an accomplishment. In 2022, Simon joined EcoSem, where he is leading a research group focused on the utilization of electric arc furnace slag as cementitious materials. In 2025, he serves as coordinator of the EU-funded EcoSlag CEM research project, bringing together 8 partners to advance innovative approaches for incorporating electric arc furnace slag and low-carbon cement. So I first met Simon probably a year or so ago at ASTM here in the States, and I think he's going to mention a little bit about some of the activity with that. So it's good to have him here today. And Simon, go ahead, take it away.
Yeah, thanks, Carrie, for introducing me, and thanks for having me. As you said, I'm not so close to the United States, but I hope this subject is relevant for you as well. So at first, you've seen my bio for long enough, I think, but I think everybody here is aware that bringing a new supplementary cementitious material to the market is not the work of one person, and we've been working very directly with the people cited here from EcoSem, the University of Toulouse, the CNRS, and Max Eicher Umwelt for this direct presentation, but there's many more to come, especially in the framework of the European project that we have started and that you will hear a bit about later on. So just as an overview, what I wanted to talk to you about today was at first a short introduction to EcoSem and our research and innovation activities, then give a small overview about iron and steelmaking slags, how they will evolve in the future and what differences there are in the major slags. Then do a short point on current EAF slag production, and then really get into the subject by talking about the beneficiation strategies that have been developed to turn EAF slags into supplementary cementitious materials. And finally, we'll have a little chat about standards and norms. As Gary said, we met at the ASTM, and that is the next big step to bring EAF slags to the market. So at first, EcoSem is mainly a European company, so many of you may not know us. We have 4 production sites in Dublin, Ireland, in Moerdijk, the Netherlands, in Forst-en-Duquerque in France, and our research and innovation happens in Paris and Toulouse in France, and Toulouse where I'm based, where we have a common laboratory with the University of Toulouse, so where we share facilities. Our total production is 2.4 megatons per year at the 4 sites. We mainly produce slag-based cements, and with substituting Portland cement by slags, we've saved 60 megatons of CO2 emissions so far. EcoSem is constantly growing. We do have about 210 employees at the moment, and different activity branches are backed by major players in the industry. ArcelorMittal as a major steelmaker, for example, in France, Saint-Gobain and Breakthrough Energy. We have participated in major projects, again, mainly in Europe. The Paris Olympic Village, for example, was partly built with EcoSem cements, but also other projects around. And we work with most concrete and cement companies to build with our cements. More precisely, the research and innovation team is quite big as well. We have 40 full-time employees, mainly based in France, and we work a lot directly and indirectly with universities all over the globe, including the US and Canada. And we have established an advisory board to enhance our way towards low-carbon cements and concretes. The European project that I was just talking about is one of the major research things we do at the moment. We've been granted 4 million euros by the European Union to bring EAF slags to the market together with different partners. ArcelorMittal, again, as a steelmaker, the FEHS, which is a specialist in slag chemistry, the HDR that will develop a specific accelerator and admixtures for EAF slag, the ETH that will look at the chemistry of iron and its mobility, the JET, which is a specialist in high precision analytics, the LMDC, whom we work together in Toulouse, will do hydration analytics, and we will do a binder formulation, upscaling, and coordination. This has started last year, so we don't have much results to share for the moment, but be aware that there will be a lot of nice things coming up. And you can follow the project either through the official European website on top, and soon we'll have our own project website with the links on the bottom left. Let's jump into the real subject of today, which is slags. I show you a scheme here of different steelmaking routes. It is a bit different between Europe and the US. In Europe, we regard the blast furnace BOF route as classic. So we take coal and iron ore, put it into a blast furnace, get hot metal out of it, oxidize the carbon out of the basic oxygen furnace, and then have the steel. And we regard steel scrap recycling and electric arc furnace slags a bit secondary. In the US, the proportion is exactly the inverse. In Europe, it's about 70-30% of the production via the blast furnace, basic oxygen furnace route, and 30% via the steel scrap route, whereas in the US, it's the other way around. All the steps where you melt the metal will produce a slag. The slag has different uses within the blast furnace or the basic oxygen furnace. You isolate the material, but also you want to purify your metal or your steel. So this is actually an engineered product that fits the quality of the metal you want to produce. If we start with blast furnace slag, for us, for a slag use perspective, it is important to note that it's produced under reducing conditions, so iron remains in the metal phase and will be separated off. The calcium-silicon ratio is usually something around 1.2, and the transition metals very mostly, apart from titanium maybe, go into the metal phase, so we don't have to deal with them. This changes a bit already in basic oxygen furnace slags, because you blow in oxygen to oxidize the carbon out of the steel. You reach oxidizing conditions, and the iron at the output of the furnace in the slag is mostly iron 3. So you have some transition metals, including iron, including heavy metal. And the other big difference is that calcium-silicon ratio is very high, around 3. And now we come to electric arc furnace slag, either from scrap metal recycling or from steel making from direct reduced iron. The oxidation conditions are somewhat intermediate. We find mainly iron 2 in the slags. We have also intermediate calcium-silicon ratios of about 1.5 to 2, and also metal oxides partially enter the slag phase. So we have to do a deal with that as well. Why is that interesting? As I said, in Europe, we regard the blast furnace, basic oxygen furnace route as the major steel making, but because of its CO2 emissions associated with the use of coal, for example, most European steel producers have announced to fade out or at least reduce production via that route, and replaces by a direct reduction reactor, which is a solid gas reaction, which will not produce a slag, and then remelting the iron and producing the steel in an electric arc furnace. The slags that come out of there will be similar to a current EAF scrap slags. Mostly the best option, and that's a large part of the discussion today, to get some cementitious reactivity out of them is granulation. And the question is acceptance by standards and norms. In terms of volume, in Europe, we're talking about 8 megatons of scrap metal EAF slags per year at the moment. The prediction of Eurofair are about 28 megatons per year from DRI and recycling by 2050. So this would be quite a bit more, 30% more than current blast furnace slag production in Europe. So this is a huge material stream that needs to be valorized, because otherwise it needs to be stockpiled or used as aggregates. And it would be nice from a cement perspective that if we lose so much blast furnace slag, that we have a new material that we can use as a cement substitute. If we have a look to the US, there are about 70 to 80 steel mills, electric steel mills, with an annual production of some 72 megatons of steel. If we do a quick calculation of about 15% slag rate, which varies a bit, it could be 10, could be 20, but we would get approximately 11 megatons of slag in the US today, which equals about twice the production of blast furnace slags in the US today. So again, this is a huge volume stream that could very well be utilized as SCM. If we look at current EAF slags here that are SEM micrographs, they are cooled down slowly, so we get a crystalline matrix and those funny white dots. The funny white dots are the iron oxides, which are not pure. I already said that it would be iron 2, so it's magnesium wüstite kind of structure, or in slag language, RO phase, with some ratio between magnesium, iron, and manganese. We would have calcium and silicon rich phases that are mostly mervanite or bridgite, so C2S structure with some magnesium inserted into there. And aluminium-rich phases, which are mostly galenite or some metallites if we mix in magnesium, but that usually doesn't happen so much. And we have most of the time some spinels, especially in recycling or high scrap metal, using EAF slags that are spinels with a high ratio of chromium in there. Giving about this overall chemical composition, this is one slag. There's some variation, but they don't change drastically. They all will have about this. If we mix the slags, if we grind them and we mix them with Portland cement, here just a simple 50-50 trial in orange, we basically don't get anything out of there. The blue bar are Bolomé estimations of the cement contribution to the mix, and the gray one is this SEM1 reference. So at 1 day, no contribution of slags. At 7 days, within the error. At 28 days, maybe a bit. As we have quite a bit of calcium in there, we tried around with alkali activation using sodium hydroxide, adding in some silicon. Basically nothing either. So the crystalline structure prevents hydration as it is. Also, if you look into the colorimetry image here on top right, you can see that if you normalize by cement, you get for the first 10 hours exactly the cement reaction from the 50% slag and cement mixes. So not even a filler effect that would result in something like this, like the green curve illustrated by quartz powder here. So for the first hours, this is clearly inert, and there's may be something coming out of the EAFs like at later ages. So if we want to use this as an SCM, we would need to enhance the reactivity somehow. And I've been taking over the subject 4 years ago now. And in the beginning, there was not much done. And if you talk to steelmakers, they weren't very happy if you wanted to change things or to work on EAFs. Like nobody really believed in it. But in the past 2 years, they got a lot of EAF slags got a lot of attention, and there was a lot of development also in the scientific literature. And for now, there is 4 different beneficiation strategies that start to emerge. The most important one, and the one I will spend most time on today, is granulation with limited chemical modification or not, which has reached by now about a TRL of 7, I would say. Then there are strategies where people try to reduce the iron and the metals out and then granulate. So this would result in a slag that is very similar to today's blast furnace slag. There's clinkerization. Obviously, you could use it as a feedstock. And there's mineral carbonation. So people let the slag react with CO2 to form amorphous silica and some carbonate phases. So I will walk you through each of them. The first one is granulation. So what you do is you have your ladle here on the left, or your electric arc furnace, depending on the strategy you're using. You will purge the molten steel, and then you have the slag. What you can do is you can either put it into a slag pit as it's done widely today, or you granulate it. There's different types of granulation that are well known, either air granulation or water granulation, to produce a more amorphous material. This is clearly the most simple and the most advanced technique because it's just really letting things flow into a granulator. However, to granulate the slag, you need to have it in the molten stage. So it needs some sort of cooperation with the steel makers, because you don't want to remelt the slag at some other place, because it would be very intense in energy and costs. Usually for EAF slag, to have high amorphization degrees and better reactivity, we'll get to that, some sort of chemical modification is necessary. Usually you need to increase the amount of network formers, glass network formers in the slag. the reactivity that you get out from quenching trials is usually good. About a bad blast furnace slag, I would say. The fate of iron and the heavy metals is still kind of a question because there is evidence that leaching doesn't happen so much of heavy metals, but there's some in there, and also for the iron you will yield a relatively dark color, and there's questions on durability, obviously. So water granulation is clearly the most advanced. I will show a video of MAU, Max Eicher Umwelt in Germany soon, but in the US there's Cocoon pushing this subject, and air granulation is mainly developed by Tinnover to my knowledge, but there may be others as well. But they are a bit back from water granulation. So as I said, this is the pilot granulator at the Max Eicher site in the south of Germany, and they kindly provided the video. So what they have the electric arc furnace inside the hall, and then they move the ladles with the slag out with this truck, and then they just pour them into this water granulator, which you can see at work there. I already said that higher amorphous content is likely very, very interesting for reactivity, and we would base that on R3 tests for the moment. We've done quite a lot of mixes in the laboratory, and we get out basically, if you get it all amorphous, you get closer to a blast furnace slag, and you start something very low here. And the amorphization very much depends on chemical modifications. This mainly concerns network format addition, but also reduction of iron in some cases. So if you dilute enough to have low iron contents, you get better amorphization. If you adapt the calcium-silicon ratio in a range that is easily vitrifiable, you will get higher amorphous content, and that yields directly higher R3 reactivity. So the takeaway here is maybe there's some chemical modification necessary to yield good amorphization, and this will depend very much on the effort you're willing to put. High modification will very likely yield good reactivity and good amorphous content, but there will certainly be places where you don't want, for financial or industrial reasons, achieve full amorphization. So there will likely be a range of different amorphization degrees in the market of EAFs. But you all know the threshold values. If we reach 300 joule per gram at the amorphization of about 60%, that is already an interesting material. Following this, we did compressor strength test at 25% replacement, and black is the neat cement bar, an orange quartz powder replacement, and gray blast furnace slag replacement. And you can see, well, for the first 7 days mostly, there's not much of a difference. At 28 days, the cement and the blast furnace substitution are more or less in the same range. And the electric arc furnace, like especially the ones with the lower calcium-silicon ratios, which will result in good amorphization, catch up quite a lot and are clearly above the quartz powder reference. We've been going a bit further with the slags that were produced by our partners and did 50-50 blends, and compared them to our slags from the FOSS plant. Again, we have somewhat less performance than in slag blends, but we have more than 10 MPa at 2 days and something around 40 MPAs for the 28 days. So this is not a perfect material, but it's clearly a usable material. And if you compare it to the 20 MPa that I showed in the beginning for the untreated slag, this is a clear gain. So granulation is a rather simple solution to the long-standing reactivity problem of EAF slags. And we'll be able to do something with them. For the moment, they are still lower, but The activation system is not optimized, and there are certainly some tweaks you can do to the system, but already at the state today, they are clearly a usable material. I talked briefly about leaching. So we have been looking into heavy metal leaching from those slags, basically those that were included in this European norm or the French standard. And what you can see is that there's many elements where there's clearly no problem at all, where you at least have a factor 10 to the regulatory value, or they're not even detectable. For many of them, this makes sense because in the first place, there's no reason you have arsenic or antimony in the slags or zinc that is slightly volatile. The ones that are logical to have would be molybdenum, chromium, and vanadium. And here again, when we look into French legislation, we're not a factor 10 away, okay, but we're clearly within the limits. Vanadium even decreases, like leaching decreases when we start modification. So modified here refers to silicon oxide addition. That means if we modify the slags towards higher reactivity, we also will get lower heavy metal leaching. So for the moment, there's clearly no environmental risk detected according to French legislation. And if we condition our slags towards high amorphization, we will get also lower leaching, which is a very positive result. There's a study from literature that pushed it a bit further. This is conducted within the Future Slag project that we have together with Tata, but not by us, this experiments. So they actually cast mortars with 25% replacement of granulated EAF slags, and then that the leaching tests according to the Dutch norm. And we see again that there's no problem for those very likely elements. The only element where they were close to the norm, as in not quite a factor 2, was barium, and there was basically no difference with the cement reference. So there's no additional risk from mortar leaching compared to neat cement, really. The other thing that is interesting, and that's maybe most interesting to note in Europe, because there's some countries that use total content limits for building materials use. There was absolutely no correlation between the total chromium content and the leached chromium content. So this suggests that you should test the leaching in actual use case conditions and not refer to the overall content. So that was it for granulation for the moment. So, and I would like to move to reduction. So reduction would start the same as the granulation. You would purge your steel, and then you would move your molten slag into another ladle where you would remelt it. And then add some reducing agent, which can be different things, really. It can be carbon, can be hydrogen, can be maybe even electrolysis. And then the reduced slag will be very different, very similar to granulated blast furnace slag would be quenched. One advantage of this is that the molten iron you get out of here, if you condition your process correctly, could be re-injected to the steelmaking process given you reach a certain purity. And that's a real concern, because if you reduce all the iron out of the slag, you will reduce also the phosphorus out, and that wouldn't be good for the steelmaking process. So likely you can't go to full reduction for chemical reasons, and there may be a compromise to be found. This process is obviously energy and CO2 intensive, but you would yield a good slag, and it will probably be more complicated to scale as pure granulation because you need a second reactor and you need time for the reduction. So this is more of a high-risk, high-gain process. To illustrate the high gain, I will cite data from literature. This comes from a paper from Tim Schade and cement and concrete research, where they compared 35 replacement of cement by limestone filler to 35% replacement by electric arc furnace slag. That was partially reduced. Again, not reduced all the iron out, but some. And they saw a clear advantage starting from 7 days in the EAF slag. So this would clearly create a more reactive material, but high risk, high gain. The next one that is always in discussion is using EAF slags as a feedstock, either within an electric arc furnace or a more conventional clinker technologies to make some sort of clinker, maybe not Portland clinker, but other clinkers out of it. And there has been some research in there. The problem mostly is that you would need to re-put the energy for the clinkerization reduction into the material. And as slag is the waste bin of steelmaking industry, there are many impurities which might not result in a perfect clinker. And there are, and also if you're using the electric process coming from a melt would yield a slightly different crystallography of the cement. So this is clearly more a clinker topic than an SCM topic, and I will not go much further into that, but that is one option that is clearly on the table. And there's active development, and there might be something coming out, but the TRL at the moment is clearly lower than of granulation technology. And the last one is mineral carbonation. You've certainly heard of this. So you would take your slow cool slag that is non-reactive, put it in some sort of reactor, add gas, maybe temperature, maybe pressure, and then yield reactive silica and carbonates. This would need high purity CO2 streams, especially when you want to carbonate magnesium-bearing silicates that need a bit of temperature and pressure. And you don't want to put pressure on a gas that contains only minor amounts of CO2 because you would lose all the energy put on the other gases. They might come from methane run DRI plants that have quite high purity CO2 streams. So for EAF slags, there's a certain logic to use this. Those techniques would also allow permanent CO2 storage and produce a carbon neutral or at best negative SCMs, which depend a bit on your process and the material source. The problem is, again, scalability. You need an additional reactor. You would need to dry the material afterwards, and it's rather fine material. So this may be a bit slow. And one point is also that in SCMs, it's rather rare to find a decarbonated source of calcium and magnesium. And here you would immobilize the calcium and magnesium that were decarbonized in the steelmaking process, though there's a bit of a trade-off. There's very much activity in this field. There's a lot of startups using it, and there might be better sources of materials than EAF slags because of the magnesium content, because of the iron content. But this is a very active field, and it might have quite interesting niche applications when you want to, when you have the boundary conditions united. Just as an illustration, we've done some work on this. What happens is if you take the non-carbonated EAFs, like here, this is a 29 silicon NMR spectrum. Your silicon coordination is in the range of Q0 to Q2 species, so relatively non-polymerized. And after carbonation, this shifts to the range of amorphous silica Q3 to Q4. So you actually produce an amorphous silicate, and you can see in the heat flow, in the accumulated heat of a R3 test, that between, in black, the uncarbonated slag and the carbonated slag here, there's a clear increase. You can also note that the increase is not as good as for granulation, but still there remains clearly a benefit in this method. Yeah, so this was more or less my technical part, and I would want to make a point on standards. As you've seen, the reactivity problem, I would say, is more or less solved, even though it's not fully upscaled. Leaching seems to be not a major problem. So if you want to introduce those to the market, you would need to have them in some standards and norms. In Europe, we have kind of a chicken and egg problem. It is hard to put materials into norms that are not currently produced. And they are not produced mainly because nobody invests in a granulator, but nobody wants to invest in a granulator because without a clear valorization pathway, the return of investment is completely unclear, and the standardization time would be quite long and no sales during that time. If you look outside Europe, there are several initiatives, and actually I learned not long ago that China has already covered the EAF slag use by an existing norm with parameters that are quite logical. They limit free lime, they limit blane surface, and they have a strength activity index criterion. The SCM has also a task group, CaO 9.27, that is preparing a specification for EAF slag use in concrete with rather similar ideas than China has. And in the European Union, there's the SystemSem project where the working group 2 collects reports on EAF slags to study their introduction into the cement norm that is led by TC51. So overall, I hope I have showed you that EAF slags are abundant resource that contains calcium oxides and silicon oxide that can be potentially used as SCMs. They have slow-cooled, a very poor reactivity, but there's different strategies to activate this potential. Granulation at the moment is the easiest in terms of process needs. You just need a granulator, costs. You just need a granulator. And technical readiness, there are at least 2 pilot granulations installed at the moment. For the moment, we, using French legislation, don't detect any environmental risk. And for us, the next big obstacle to tackle is the introduction into standards and norms. So I'm at the end of my presentation and would be happy to take questions if there are any.
Thanks, Simon. That was very good presentation. Appreciate it. Very informative. I have myself a lot of questions, but we do have a bunch of folks online who have also submitted questions. But I guess to kind of start it off, and Sarika and I will kind of field those questions for you so you don't have to worry about going into the Q&A box. But I'm curious, you mentioned here at the end on the standards. So you have your EcoSlag CEM project in Europe going. You mentioned in China that they've already kind of looked at some standards and some of the information they're looking at. And then you mentioned, the work possibly looking into a standard with ASTM here in the United States. So going back to the project in Europe, what are some of the goals of that project work? Do you have some specific goals that you want to achieve, like the standardization, some of these items you brought up with the different mechanisms? What are some of the key ones you're looking at? And do you see something like that could occur somewhere outside of Europe, that type of collaboration group?
Sure. Well, to start with the ambitions of the European project, has clearly a technical focus. So we're looking into optimizing the granulation parameters and the cement formulation to get higher performance cement out of that than we have at the moment. The European Union clearly proposes interaction with legislators as well for people that have European projects running. So we're hoping that this will facilitate standardization, but the project does not directly aim to put it into standards. It will lay the databases for some sort of either standardization process or a certification via national mechanisms. We've done that in France, for example, for our Ecosym Act technology, where we have a permission to use cements outside of the standards.
Okay.
And yeah, if that could happen outside of Europe, I think yes, very much. I'm not so much aware of research funding available in the US, but I think close collaboration between cement makers or concrete makers and steel makers can very readily happen. And I think we have a common interest, the steel makers, to evacuate their slags at a higher value, and the cement and concrete people to have new SCMs available.
So maybe a call to action there from Simon.
Clearly.
All righty. Okay. A couple questions here. Sarika, do you wanna grab one of them first and bring it up?
All right, let's try this one, Simon. Thanks again. Do you have a comparison between the granulation grade and the reactivity achieved with MAU technology compared with other technologies such as, I believe it's Cocoon?
Cocoon. Mhm.
Also about the complexity of each technologies.
No, we don't have a direct comparison. We didn't look so much into the technology of Cocoon. The results that we saw at conferences are rather similar. I don't think that the big difference, I think, is the modification strategy, not the quenching so much.
All right, thank you. This one, maybe you already mentioned, not sure, but let's give it a try. I believe that the global EAF slag is around 200 metric tons per year. Is that correct?
Metric tons, certainly not. It's clearly megatons.
Oh,
Megatons.
I'm sure it's megatons. Maybe that's what it means. Yeah.
I'm trying to do the math. Yeah, that sounds not too far from reality. Yeah. I don't have the number ready, but that sounds about the order of magnitude.
So
All
Simon,
right.
there's a question here regarding the use of EAF's slag and any comparisons, actually calculations, and looking into the embodied carbon. So if we're going to be substituting and using this material, how does it impact the embodied carbon? Obviously, with different technologies, it's probably going to have a variation on that. But what have you looked into that regarding that so far? And what do you know? What can you share?
Well, that is a bit of a complicated and somehow political question because, for
Okay.
example, in France for blast furnace slag, we practice economic allocation, not physical allocation. So it's completely unclear the amount of CO2 that will be allocated to the slag. The slag will be mostly well, it will be less CO2, will have less CO2 in the embodied than the blast furnace slag because the process is already less.
Mm-hmm.
At the moment, as the value it sells at is very low, the embodied carbon will be just very, very low, but that would evolve obviously with market introduction of SCM use. And then the other big question, obviously, is the substitution rate you can achieve, and that very much depends on the performance indicators we're looking at.
Absolutely. Sarika, you see any more in there? A couple more.
Couple more. Any possibility of ASR in slag incorporated concrete?
Of
ASR.
ASR.
Yeah. We haven't seen that at all. I wouldn't exclude it completely, but the point is that the glass you produce is relatively rich in calcium. It should react into CSH rather than retarded expensive silica gel. So I think the risk is very limited, but I can't fully exclude it.
Thank you. Carrie, did you touch the last question?
No, go ahead. The last one.
Okay.
Yep.
All right, let me read. In one of the slides, you mentioned to chemical modification to increase the reactivity. Can you explain what kind of chemical modification has shown positive results?
Question.
Very foremost, it is addition of some network forming iron into the slag. The difference with blast furnace slags, for example, that you get to vitrify 100% is very much the ratio between calcium, magnesium, and silicon, where silicon is the glass network former, and magnesium and calcium, the network modifier ions. So there's a bit of a trade-off. If you don't produce, if you don't have enough network formers, you will not be able to create a glass network and vitrify the slag. Whereas if you have too much network formers, you will have a glass that is relatively non-reactive. So yeah, as it is for the most slags we see, the calcium silicon ratio is a bit too high to vitrify. So you would need to add silicon oxide mainly.
Thank you. This kind of goes with the same one. What about the chemical activation of SS, like use of EDTA or some other chemicals?
Yeah. I'm not quite sure if this refers to crystalline slag or to already glassy slag. The point of EDTA is that it's a very strong complexant of bivalent cations. So it will kind of purge the calcium out of the system. This is usually a retarding effect on cement. You could eventually use the strategy as a pre-treatment, but I think the relation between effort you need to put and the cost of the treatment would not be, and the result of the slag would not be very good. And yeah, mixing EDTA with common slags is usually a retardant.
Excellent. A lot of chemistry involved, right?
Yes, there's lots of chemistry. It's good stuff. So I think that wraps up all the main questions we had in there. Some of them were similar, so we kind of combined them into one. But we thank you, Simon, for this really informative presentation. And I think on the, I don't know if on the first slide or if we have one here, contact information for you in case anybody has any further questions. I believe we can, I don't know if we have that on a slide here, but we can,
Yeah.
share that with folks
Sure.
who may want to follow up with you on some of the work you're doing in Europe. So that would be great. If we want to go to the next slide, we'll kind of wrap things up.
There we go. Okay, thank you again. Thank you again. My video on. Thank you again, Simon. Please visit the new website at newconcrete.org for resources on low carbon concrete production and placement. The website provides access to our sustainable concrete guides, frequently asked questions, webinar recordings, and more. And the QR code shown on the screen will take you to our bookstore where you can purchase, if interested, the news recently released Low Carbon Concrete Guide. And if you can go to one more slide, we'll wrap it up there. Here we go. Please join us for news next webinar with Ash Grove, presented by Mike Fedorko on June 25th, 2026. And thank you for attending today's webinar. Please stay tuned for our future webinars. Thank you again, Simon. Thanks everyone for joining.
Thank you very
Thanks
much,
for having me.
everyone. Thanks.
Thanks, everyone.